Okay, good. So, I don't know, if you have never seen XKCD, this is a wonderful way of wasting your time and having fun. And sometimes they actually explain math and statistics in an interesting way. So I guess you may have seen this cartoon. What I'm going to get to though is this one here. So there's this wonderful slide about jelly beans cause acne. And scientists investigate, and, well, we found no link between jelly beans and acne. But that settles it. And then, well, they go and investigate. And so here's what happens. I'm not going to read you all the 20 pictures, but basically it goes like, well, we found no link between pink jelly beans and acne, or orange jelly beans and acne, and that at, a confidence level of 0.05. And then, well, voila, there's this one bit, namely green jelly beans and acne. Actually, well, there's a link at confidence level of 0.05. And so now you can infer that, with 95% confidence, you can have a wonderful news article which shows that there's a link between green jelly beans and acne. So I guess we all know that this is, of course, bollocks, right? Does somebody have an idea of what happened here? This is actually a really important concept. Okay. Yes?
Under the frequentist interpretation of probability, if you run an experiment or multiple experiments multiple times, under a 0.05 confidence, about 1 in 20 results will be spurious.
Correct. So basically, what happened is we had a confidence level which in 1 out of 20 cases would fail. And we ran 20 cases, and lo and behold, well, 1 went wrong. Well, we could have gotten lucky, and none of them would have failed. It could have actually also been the case that more than 1 would have, failed. So what basically happened is we had an interesting test, which was not too bad, and we invoked it too many times. This is just like if you roll the dice often enough, you will roll a 6. Right? You just have to be patient. So that doesn't mean that 6 is a very common outcome. It's as common as any of the other numbers. But if you roll it for often enough, you will find one. So this is called multiple testing. And you actually need to account for that when you do your statistical analysis. So there's something called Bonferroni inequalities. And they essentially deal with these problems. Let me just write the name out. Yeah. And so if you want to impress somebody, you talk about the Bonferroni inequality. Otherwise, you could talk about multiple testing. Or if you, for instance, read the VC literature, this is called the union bound. So it basically means I have 10 different outcomes, and I want to bound the probability that any of them will occur. And that's, of course, upper bounded by the sum over the probability of each of them individually occurring. Right? And that bound holds regardless of whether those outcomes are dependent or independent. So we'll get to that, and I think we'll actually get to that specifically in homework number 3. So remember this. Now, let's start really gently, namely with probabilities, right? So what are probabilities? Well, let's say we have a space of events, and those could be discrete events like the server is working, or it responds slowly, or maybe the server is broken. It could be something that's continuous, like, well, the income of maybe the user using my website. Or it could be something in some, discrete, very interestingly structured domain where, for instance, somebody searches for a statistics tutorial. And so basically I have a space and have a measure on it. And if you really like the intricacies of this, you should take a class in measure theory. But it will not help you very much for this class here. But if you're really into the specific details, and sometimes if you're a statistician, you will really care about those things, then you should take a class in measure theory, and a lot of things will become a lot more clear. In any case, what we have is that we have a space of events, let's say X, and the probability of any of those subsets of events is contained in the set between 0 and 1. And furthermore, the probability that something happens is 1. And also, what I have is that if I have disjoint sets of events, then the probability that something happens in the union of those sets is given by the sum of the probabilities for each of those sets. These are the probability axioms of Kolmogorov. Now, for instance, I could have something like the probability that my server is working is 0.99. I could also have something like that the range of the user having an income between $90,000 and $100,000 is 10%. Quick question, why does it not make a lot of sense to ask what is the probability of the user having $90,001? Why do you think this is a bad idea? Well, you already answered the previous question. Somebody else, please. By the way, thanks for raising your hands, but okay.
Well, if you assume that the income is continuous, then probability is 0.
Exactly. So essentially, that's the right answer. If we assume that we have a density over incomes, then the probability of any point event is 0 unless I have a point mass in my distribution there. In practice, it means, well, there will be extremely few people who earn exactly $90,001. Right? So this is why if I have continuous random variables, and unless I know that I have point masses, intervals, and that in that case also sets that are not of measure 0, make a lot more sense for queries than point events. Okay. So then let's do something very simple, and this actually is sometimes kind of useful if you want to look at intersections and all that kind of stuff. So this is called a Venn diagram. If you never heard of it before, well, okay, there it is. It's basically a space of all events. The outcome's x, the outcome's x prime. And if I want to ask things like, well, what's the probability of the union of x and x prime? So that's basically this purple area plus that purple area. It's, of course, the ellipsoid plus this rectangle minus the intersection. And so by rearranging things, you can, of course, also work out that the probability of the intersection between x and x prime is the probability of x plus probability of x prime minus the probability of the joint. Right? So you can just rearrange those things. So in case you're not quite sure, draw the picture, and you will never get it wrong. Next thing to look at is independence. So suppose I have two random variables, x and y. Then they are independent if p of x and y is given by p of x times p of y. So where could this happen? For instance, if I have two users who log in, then approximately their login behavior is independent of each other unless they live in the same household or something like that. And this crashes in different colos are approximately independent. Well, it's not entirely the case because maybe you had a power spike and something really horrible happened. But basically, your disks in different server centers may fail at approximately independent times. Now, independence is a really good thing because it allows us to simplify a lot of the representation. But in some cases, you really want to have dependence. And as a matter of fact, in almost all cases, there will be dependence. It's just that quite often you can approximate it away. So for instance, if you even think about the login behavior, usually when you guys log in is independent of each other, but if suppose I don't show up, then you will probably all go on Facebook and email and Gmail or whatever and read your latest messages. So your behavior in that case will not be independent, but it will be only conditionally independent, conditioned on whether I show up in class or not. Right? So dependent events, emails for instance, there will be a lot of dependence on external events. There will be maybe if I send you an email and you send me one back, then if I send you a really nice email, you will probably reply back nicely and vice versa. Right? Queries, you might search for something, and depending on what you see in the first query result, your second query result may be different. The news stream, buzz, tweets, all those things are dependent on each other. Here's another case, Russian roulette, right? So if you, I guess everybody knows what Russian roulette is. You have a revolver, you spin the barrel, and of course you put the bullet in first. You spin it, and then you fire. And so, well, maybe you survive the first thing. Now, should you spin the barrel again before you fire again? Who votes for spinning it again? Who votes for just firing a second time? Firing the second time is a really bad idea. Let me show you the example of why this is a really bad idea, and for whatever reason. Okay. Sorry, for some reason it keeps on dropping the connection. So if this is, our stylized revolver, and here are, the cartridges. And so this is, of course, the one that's going to kill you. And if I spin the barrel in a random way, then I'm going to end up in 1 out of 6 positions. Okay, so conditioned on the fact that I survived the first trigger, it must be in one of those 5 places. 1, 2, 3, 4, 5. Okay, could be in any one of those. Now, since I don't know where it is, after all, this is Russian roulette, it means there's, with equal probability, in 1 out of those 5 cases, the next bullet is going to kill me. So in other words, the probability of me dying the second time is 1 over 5. Whereas if I spin it again, the probability of me dying is 1 in 6. So you have a slightly higher chance of surviving the second attempt at stupidity if you spin the barrel again. Of course, you should never attempt Russian roulette, but this is an interesting example of where you have dependent random variables and in a dependence that, is a little bit less trivial. Okay, good. So, in other words, dependence is everywhere. Now, let's actually use this. So, basically, let's suppose that there is, somewhere in the universe a God that decides, well, I'm going to send you spam or ham. Okay. And so that God goes and, tosses a coin and decides, oh, okay, I'm going to send you spam. And then, it generates a mail. So what you basically can now do is you can model the joint distribution over spam and emails as the probability of a spam times the probability of, or the density in this case, of a particular email given spam or given ham. And so what we've just done is, intuitively, we've just looked at a special instance of Bayes' rule. Okay. So if I have the joint probability P of x and y, I can write it as P of x given y times P of y. I can also write it as P of y given x times P of x. Just by symmetry, because there was nothing special about x and y, I can write it in both ways. And then, of course, what I can do is I can go and pick out this term here, which goes here. And then I go and collect everything else in here. So in case you ever aren't quite sure about Bayes' rule, just re-derive it this way. I think I've done it more often than I would be non-embarrassed to admit, but basically make sure you get that right. Now, why is this so powerful? Because it basically means that if I have a model of how things happen, and if I have a model of how the causes are distributed, then I can turn this around and I can say, well, can I estimate the cause given the observation? Okay, this sounds amazingly abstract, and let's look at a specific case. So I can basically use this to test hypotheses and so on. So let's pick something a bit more well, closer to home. So let's say I did something naughty and maybe I need to go and have an AIDS test done, right? And let's assume that I live in a country where 0.1% of all people are infected. Okay. Let's assume that I go to the doctor and the doctor actually administers a test, and the test is really good because it will pick up whenever I actually have AIDS. Right. However, there's a catch. This test has a fairly high false positive rate. It will report positive for 1% of all healthy people. Okay. And so, now what I might do is, I might ask, what is the probability that I actually have AIDS if the test comes back positive? Okay. So this is exactly what we have from the previous scenario. So why is that the case? Well, first of all, let's look at, P of AIDS given test. That's what I'm after. So by Bayes' rule, this is given by P of test, given that the outcome is AIDS, times the prior probability of me having AIDS, divided by the probability of the test coming back as positive. Right? Any questions at this first step? Because this is really important. If you get lost here, then you will have a lot of trouble later. So what we are basically now going to work out is what P of test being positive is. And of course, I can write this as P of the test being positive, given that the person has AIDS times the probability that the person has AIDS, plus the number of cases that the test comes back as positive, given that the person doesn't have AIDS. Right? And now this is exactly 1 times 0.001. That's, the prior probability of somebody having AIDS, because we had 0.1%, divided by, all the cases that, that the test really properly detects, so that's the same thing in the denominator, plus all the false positives. And this is the one term that is going to swamp everything. Because even though we only have 0.1% of all people being sick, we have a false positive rate of 1%. And so the second term here, so basically that term, is really going to swamp everything. Because it's 0.01 times 0.999. And if you look at it, you come back at, well, the probability that this person actually has AIDS is about 9%. This is amazingly counterintuitive, right? Because you would think, well, if I have a test that, has a false positive rate of 1%, and I know that it detects all cases of AIDS, then common sense would suggest that if the test comes back positive, well, you're actually going to be sick. But it just means because the prior probability of having AIDS is very, very low, this doesn't happen. Now, if I was somewhere in, let's say, the south of Africa, where you have 20-30% rather than 0.01% of all people having AIDS, then this probability would change quite a bit, right? Because then this number here, this would be much smaller, whereas this would be larger, right? So that's basically why your prior probability really drastically influences those things. Now, this sounds like a really obvious, trivial case, but a non-trivial number of people have been convicted erroneously of crimes because of DNA testing, where exactly those prior probabilities were not properly taken into account. Because a lot of lawyers aren't so good at statistics, or judges, or whoever. Now, of course, the point is, this is kind of terrible, but what am I going to do now? I'm probably going to go and have a second test done. And that second test is actually not so great. Of course, all those numbers are entirely made up, and nowadays AIDS tests are way better and all that, so you shouldn't be too worried. But, I just want to make an example that gets everybody's attention. So let's say I do a follow-up test. And that follow-up test reports positive for 90% of all infections. And it reports positive for 5% of all healthy people. So this is actually a really lousy test. But, OK, let's just use it. And let's suppose it also comes back as positive. So again, I work out those numbers. And I take the product. And now I'm getting something in the order of almost 36%. Now, 36% is where you should really start to worry. Now, AIDS maybe has better tests, but if you have sometimes cancer diagnosis, those error probabilities are not uncommon. So this is why when you come back with a positive or negative diagnosis from something, it doesn't always mean that you have it, and you should not get mad at your doctor if he tells you, well, the test came back one way or another. Okay. So here's the question. Why was I allowed to use that second test? What assumption did I make on the second test such that I was actually allowed to use it? Yes?
That test is independent from the first one?
Exactly.
And so the results are going to be correlated by the same fault in the assumption?
Exactly. So the key point is the test is conditionally independent. So conditionally on me having AIDS or not, the outcomes are independent of each other. It doesn't have to be strictly independent. As a matter of fact, if that were the case, it would be kind of bad because it would just report random numbers in either way. But conditioned on me having AIDS or not, the outcomes will not be correlated. So, because otherwise, why couldn't I just go and use the same first test twice? After all, it's a much better test than the second one. And if I could make the assumption that those things are conditionally independent, I could really rerun the first test twice. But obviously, that's not the case. So conditional independence means the same thing as independence, just that you now have a conditioning variable. So conditioned on, let's say, AIDS, the outcomes of test 1 and test 2 are independent of each other. So sometimes statisticians write this as follows. They write this as T1 independent of test 2 conditioned A. Yeah. So that's just a short form of writing this equation here. Okay. Now, before I move on further, let's have a very short public service announcement in the context of dealing with probabilities. And I'm telling you this because if you don't take care of it and you implement stuff with probabilities, you may end up with horrible outcomes and not know what's going wrong because your code is mathematically perfectly correct, and it will produce perfectly wrong results. So what happens is that when we work with probabilities, especially with unnormalized probabilities, where sometimes those unnormalized probabilities can be very large or most likely very, very small numbers, then what really happens is that you can get numerical underflow or numerical overflow. So who has taken a class that explained floating point representations in a computer? Awesome. Okay, so therefore you all know what an exponent is and a mantissa and the sign. So the sign is just whether it's positive or negative. Mantissa is where you really have all the information stored about the variable, and the exponent is basically something that you can use for the magnitude. And what you can see is that you have 5 times as many bits for the mantissa than what you have for the exponent. So that means, well, you can't really deal with numbers that are much smaller or larger than, basically about 2 to the 30 or 2 to the 40. Sorry. No, about, maybe this is about 1,000, right? So if you have an exponent that's smaller or larger than that, you run into trouble. So this means in practice that you can very well run into trouble with numerical overflow and underflow. Now, there's a very easy way how to deal with this. You basically don't store probabilities, but you store the logarithm of those probabilities. Because in that case, the exponent now moves over into the mantissa. So if you have really large numbers like 10 to the 100 or something very small like 10 to the minus 200, all of a sudden you now have, let's say we take log base 10, you're basically dealing with numbers between 100 and minus 100. So this is much, much easier to deal with, and we don't need the sign anyway. So we're making extra use of this. Now if I have products of probabilities, this is super easy, right? So, I mean, what I'm doing here is I'm setting pi equals log p, and then of course the product just becomes the sum. Everybody knows that. Now things get a little bit more interesting if I have sums of probabilities. With sums now are really awkward because now I cannot just go and sum those terms together. After all, I used that already for the products. Now what I would have to do is I would basically have to perform sum of e to the pi I and then compute the log of this. But this is a real problem because e to the pi I can give me numerical overflow or underflow, so I'm no better off than before. However, what I can do is I can simply go and pick the largest term among all those pi i's. So basically I take max I of pi I, and then I add to that the log of e to the pi I minus the maximum. So now all those numbers here will be less equal than 0. And one of those numbers is going to be exactly 0. So I basically get the log of the sum of basically 1 plus a whole bunch of numbers that are a little bit less than 0. So I will never get overflow. And furthermore, this range is reasonably well calibrated, because if all the numbers are really small, then at least I'm now summing in the properly calibrated range between these numbers. So this is quite useful. Okay. Now, what I can then do next is, well, I just store the log again and happily move on. So this is useful when you do dynamic programming later on, for instance, in Markov models. Always make sure you don't get overflow or underflow, because otherwise you get division by 0. So this is just a general public service announcement. It doesn't directly relate to Bayes' rule, but as soon as you introduce probabilities, you really need to be very, very mindful of this. And yes, I fall into the trap myself. I've written code where I didn't take care of this because I thought it's going to be fine, and then the code fell over. And pretty much every one of us will do that once in their life because we get reckless. So don't. Okay, good. Any questions about this? Okay. So let's look at spam filtering. And yeah. Sorry, somehow the tablet doesn't synchronize very well with my laptop today. So the first assumption that I'm going to make is, because we're going to build a NaiveBayes spam filter. Sometimes people talk about a Bayesian spam filter, and what they mean is really a NaiveBayes spam filter. So you can do a lot of other Bayesian things than NaiveBayes. NaiveBayes is actually not very Bayesian at all, but it just uses Bayes' rule. So the key assumption that I'm making is that the words occur independently of each other, given the label of the document. By the way, you're going to have a lot of fun with that in homeworks 1 and 2, because it's actually an important concept. So essentially, this is the same thing as what we did before with the AIDS test. So with the AIDS test, we basically used each individual test as a way of measuring whether the person has AIDS or not. Here I'm using each individual word as a test to infer whether the email is spam or ham. Same thing. And so I'm making the assumption that P of W1 to Wn, so the probability of all those words in an email, given spam or ham, is given by the product P of Wi given spam. And then I just go and invoke Bayes' rule. And that means that I can just work out that P of spam, given all the words, is proportional to P of spam times P of Wi given spam. So why did I not have to use anything in the denominator here? So basically, why did I not have to normalize? Or how am I going to normalize later? Any suggestions? Yes?
Because we only have two things we care about, spam and ham. And because we're going to have something proportional, if we're so inclined, then it doesn't really matter what they're both divided by.
Correct.
They can both be divided by 5 million and it doesn't change it.
Correct. So just to repeat it for everybody, this is exactly the right answer. Perfect. Thank you, by the way. Essentially, we only have two possible outcomes. More generally, if you want to infer something, then you can always recompute the normalization explicitly by just taking the first two terms in Bayes' rule, evaluating it for all possible outcomes, which would be, spam here, right? And then just putting it into the denominator, normalizing appropriately such that everything sums up to 1, because we know this is a probability, so it has to sum up, and then I'm fine. And so now, if I want to actually do something useful with it, I need to go and compute the spam probability and the word distributions for ham and spam. Now, computing spam probabilities are easy, right? All I do is I just look at, let's say I use those emails, count the number of total emails, count the number of spam, count the number of ham, and voila. So this is kind of okay, but a couple of things can go wrong. Let me show you, let's say, a couple of spam emails. I mean, they're not real spam, but just to get the idea across. So get rich quick and, buy your CMU stock, or, maybe some Viagra type reference, or maybe, some degree mill which wants to give you a PhD from Central Michigan University. Okay, so no, they don't give that out. And at some point, I had an interesting argument at a conference why there was a difference between Carnegie Mellon and Central Michigan. Yeah. Not the best conference to attend. But the spam filter doesn't really care about the logical coherence between, the words in the text. So in other words, you could, quite reasonably concoct something like make your rich CMU PhD experience last longer. Well, yes, of course, you want to get a really great PhD, but basically, this is a completely nonsense phrase. Yet the spam filter will consider that just as much spam as the first three, whereas any human will immediately say, well, the first three kind of make sense in their nonsense, whereas the fourth one is just nonsense. So what's going on? So basically what happened is, sorry. Okay, don't know why my presenter isn't working well today. So I'm basically making the assumption, and this is just the first graphical model that we're going to encounter, and we will see a lot more. But this is already going to explain a lot of the prototypical things in there. You basically have a variable, causal variable, in this case spam, and this causes various words to occur or not occur. And so I can actually write this out as P of W1 through Wn given spam is the product of the P of Wi's given spam. And since, well, statisticians are just as lazy as computer scientists, they've invented their own for loop. And this is a for loop in statistics. It's called a plate. You will see this a lot. So if you've never seen this thing before, or if you've ever seen graphical models of that form, and you always wondered what this box was about, That just means for I equals 1 to n, do this to that variable. Now, the really cool thing about plates, as we will encounter later on, is that you can have nested loops, but you can also have intersecting loops, something that's really awkward to implement with code, but that's really easy to write in statistics. So remember the awkward to implement in code and really easy to write in statistics? If you actually want to do inference in it, that's really what will happen to you when you program it. It'll be a bit awkward. But it just means that now I don't have to write out each variable individually anymore. I can just write it like so. And if you've never tried doing this in LaTeX, there's a package that you should absolutely learn about. It's called TIX. And it has about as user hostile error messages as you could wish for, but you can make really nice graphs with it. Okay. And so, yes. Now, of course, the last bit that we're missing is how do we actually get P of word given spam, right? So I kind of, weaseled my way out of the argument how we get P of spam. But how do we get the word distribution for spam? Let's look at the data a little bit more closely. So the first thing that I have is I have my emails. Right? They have a header and body and metadata and so on. It's quite structured. I have the labels, assuming that the users actually label all the emails. Who labeled an email as spam or ham yesterday? Wow, that's only 2 of you. Or 3, maybe. I also did. So do that. Your own spam filtering will improve. And you also help everybody else. So do something good for your email provider today. Spam label your emails. Now, one thing that you also need to do is you need to be able to handle a lot of emails, billions of them. You might have 1,000 servers or more. And what we need to do is we need to estimate very efficiently P of y and P of xi given y. We need to compute the distribution of xi's for every of those y's, and we also need to get P of y. So what does the data look like? If you, at some point, look at your mail client, you have it display the raw source, then you see that in addition to all the text that you might really care about and visualize, there's this huge trail of where the email came from and who sent it, and basically a lot of stuff that actually is engineered a little bit to keep the spammers at bay. And so what you want to do is you basically want to process this efficiently. So let me quickly give you a preview of how you can do this with, let's say, MapReduce. So MapReduce is one of those mechanisms where you might have hundreds of faulty computers. Lots of the jobs are almost embarrassingly parallel, like, for instance, except for sorting and transpose. And you have exactly 2 types of operations, map and reduce. This is actually the really ingenious part in MapReduce. The fact that there exist those 2 very simple operations that cover a lot of interesting algorithms. So the brilliant design in MapReduce is not that it's super complicated and amazingly complex or whatever. The brilliance is that they realized, so they in this case being Jeff Dean and Sanjay Gemawat, that there are essentially 2 operations that will allow you to implement a very large family of algorithms efficiently, more or less efficiently, and therefore, cover, I don't know, maybe 1/3 of all the tasks that you might have in a large internet company. It doesn't cover every problem that you might encounter, and companies that try to solve everything with MapReduce usually don't do terribly well. There are some examples, and you can find them on the web. But basically, map does the following thing. It takes a key and a value. Key might be a document ID. So in this case, we don't really need it. But in another case, for instance, you might actually have different users and so on. And it emits key value pairs. Let's say, for instance, word ID and count. Word ID is the key, count is the value. Reduce then aggregates all the key value pairs with the same key to the same machine. Doesn't guarantee that this machine might not get a lot of other stuff, but at least all the keys, key value pairs with the same key go to the same machine. So for instance, all the keys with the word machine in it will go to, let's say, machine number 42. And then reduce goes and aggregates all of those. So let's see what happens with NaiveBayes. So if I have two classes, spam and ham, and have binary features, just whether an attribute is present or absent. So I'm really very drastically simplifying it. Then one way that I could do is I could actually just count the occurrences of features for ham and spam. And then I count the number of ham and spam emails, and I just take the ratio. So therefore, all I do is I just have, p of xi equals true. It's the number of times that I occurs for, y, divided the number of times that y occurs. So let's say I count the number of times that CMU occurs in ham, count the number of times that CMU occurs in spam, and I get the corresponding word probabilities. Okay. And then I'm basically done, right? Now, what could possibly go wrong if I did this? Right? Because now, of course, P of y given x is proportional to ny over n, so that's not going to be that's going to be a reasonable number. And then I have basically the ratios of the number of times a particular word occurs divided by the number of times spam occurs, and correspondingly for ham. So what could possibly go wrong with that last line? Any suggestions? Okay.
So the word may not appear in one of them.
Exactly. So a word may not appear in one of those cases. Well, that's okay, because maybe I know that if the word Viagra occurs, it's always spam. That's okay. And it never occurs in ham, because you will probably never see that word in communications from CMU, from the administration. At least you shouldn't see it unless something is badly wrong. Okay. But what happens if a word never occurs? Okay, so let's say the word never occurs, and then maybe our biologists figure out that Viagra can cure cancer. And CMU wants to make this amazing announcement that our biologists found out that Viagra cures cancer. Then your NaiveBayes classifier will infer, because Viagra never occurred in emails from CMU, and we've only seen it in spam. So therefore, this email must be spam, and it has no other choice, because it never saw it before. Likewise, if it always occurs, and at some point it doesn't occur, it also can go wrong. And those are exactly those two cases. That's basically Viagra cures cancer, and that's a CMU email from the dean's office without CMU in it. If that never occurs, then all of a sudden you get an email from the dean without that in it. You might infer that maybe it's not from the dean. Right. That's a much less likely case. This can happen quite a bit. Now, things can get even worse. You can have an email where all of a sudden a word that never used to occur in a ham email occurred in spam, and a word that never occurred in spam occurs in the ham part. So I basically have a 0 for P of spam and a 0 for P of ham. And so I get 0 probability for both ham and spam, and I just don't know what to do. So what went wrong? Does somebody have an idea of where we goofed up? So is it really true that you could never see an email containing Viagra from CMU? Well, that's probably not true. It's just extremely unlikely. So my prior assumption is that, well, it will almost never occur, but it's not completely excluded. So in other words, we should never set the probabilities to be 0 or 1. And this can be fixed. So the way how you fix it is essentially as follows. You, instead of taking n of I and y over n of y, you add to this plus some small alpha I, and here I have the sum over all j alpha j. So basically what I'm doing is I'm adding to my counts a small extra, such that the zeros now turn into something that's still quite small but not quite 0 anymore. And of course I need to normalize appropriately in the denominator to make sure that the probabilities sum up to 1 again. And that looks like cheating, right? Basically I'm just hacking the numbers not to get 0. Who's ever done this with, let's say a document classifier, and you took logs of word counts, and of course log of 0 is really bad, so you just added 1 to all the word counts. Who's done this in the past? Yes, you have. Anybody else? Great. Okay. So what you just did is you were quite solidly in the footsteps of Monsieur Laplace smoothing. So this is technology that's over 100 years old. Basically, all he did is he just said, well, let's add something small to the counts. Now, that sounds quite magical. It actually turns out that there's a really nice mathematical reason behind this. And what you're basically doing is you're imposing a conjugate prior on your observations. We'll get to conjugate priors and so on at the end of the statistics block, so don't worry. We'll see that in explicit math, and you'll probably have fun with the Gauss-Wishart prior at some point in your homework. Did you have a question? No, it could not. Well, it might not be 1 because now you're adding a small constant also to the other part, right? So let's say I encounter Viagra 10 times for spam and 0 times for ham. And I'm adding a count of 1 to each of those. So I have 1 and 11. But now I need to divide by 12 because I have 10 plus 1 plus 1, right? And so I get the probability of 1 over 12 for ham and 11 over 12 for spam. So this is why I'm solving the effects at both ends by essentially smoothing. So what I'm basically doing is I'm inventing fake additional data in order to make things go away. And that is a very, very common strategy, to add fake data to your sets of observations, to regularize, to penalize, to smooth out. And depending on how clever you are with fake data, you can actually get quite astonishing results. So for instance, those of you who may have read the news last week, Baidu just got this nice result about having the best performance on basically ImageNet, on object recognition. And essentially the reason how they achieved it is by adding fake generated data to their data set to augment their data set. And that gave them a substantial boost. Okay. So now let's see how we actually implement that in practice. By the way, thanks for the question. So here's the basic algorithm. I just go, and for each document, I aggregate the label counts given y. So basically, I store how many times each word occurs for ham and spam. I do that for each of the features, and I aggregate this statistic basically just, for all the pairs xi and y. Then for the y's, I just estimate the probability p of y. That's basically ham or spam. And then I just now need to merge all the documents in order to get something. And I might, for instance, if I have a continuous distribution, I might use something like Parson windows, which we will get to in a few lectures, or use an exponential family estimate or whatever. And then I can just happily go away. And the good thing is, this can be done very, very efficiently in parallel. Because this pass through all the data, well, I can do that in parallel over many machines. The aggregation on a per word or per key basis, I can also do trivially parallel because each key is dealt with independently of each other. And so, I can do this with MapReduce. So if you've never used MapReduce in the past, you should probably install something like Hadoop on your computer. If you have a Mac or a Linux box, that's very easy. It's basically apt-get install Hadoop or sudo port install Hadoop, and that's about it. That's all you need. If you have a Windows machine, you should learn Unix. Yeah, sorry about that, but this won't be the last time that you will need to learn how to deal with Unix. Yeah, maybe there is some version of Hadoop also for Windows, but even Microsoft Azure offers Linux for that purpose. Yeah. Okay, so this is really the basic template, and this is one of the simplest MapReduce algorithms, and if you do it well, you get a passable spam filter. Okay, any questions about that so far? Okay, good. Because what we're going to do now is we're actually going to go into the business of estimating those probabilities. Because I sort of kind of alluded to it. Well, we'll need to get, this term here, right? And I didn't really tell you very explicitly, how we do it, why this is a good idea, and why, you might actually want to do that. So let's look at estimating probabilities. So, why is this heuristic that I just told you before, where we go and, take, counts for positive, counts for negative, or heads and tails, and we just write those probabilities out. And the reason why I'm going to do something very trivial now in an excruciatingly complicated way is because it's the simplest prototype for then much more interesting reasonings. So let's say I have really two outcomes, heads and tails. And I want to, so I can go and write out the data likelihood. So likelihood is basically the, given the parameters, how likely my model explains the data. It's different from a probability. Okay. Now, what I can therefore do is, it's basically, if I have those various events, I have just, pi raised to the power n1, 1 minus pi raised to the power n0. This is if I have, an explicit sequence of all those outcomes. If I want to deal with, all possible sequences, then I have to, use combinatorial coefficients with that. But let's, for the moment, assume that I know exactly, what the values of x1, x2, up to xn are. So it's really, pi to the number of times that, a 1 occurs, times 1 minus pi, because that's exactly the probability of zeros, raised to the power n0. And so now what I want to do is I want to optimize over pi to find the thing that maximizes the likelihood. But the problem is that, this pi has to be between 0 and 1. So it's a constrained optimization problem, and constrained optimization problems are awkward. So what I can do is I can basically, for instance, say, let me reparameterize this by writing, pi as p of x parameterized by theta as e to the x times theta divided by 1 plus e to the theta. This is probably the most complicated way how you've ever seen a number between 0 and 1 written, right? So, x can be 0, 1. So this is heads or tails. This is x. And theta is basically what parameterizes things. Now you can immediately see that if theta equals 0, then e to the x is going to be x times 0 is going to be 1. And down here it's going to be 1 plus 1, so I get 1/2. So for theta equals 0, I get the case where both events occur with equal probability. For theta going to infinity, I'll get the case where x equals 1 occurs with probability 1. For theta going to minus infinity, I get that, well, the zeros occur with probability 1. So what I've just done is I've reparameterized my domain in such a way as to turn the constrained optimization problem into an unconstrained one. It actually turns out that this is a particularly nice parameterization. It's called an exponential families parameterization, and we'll see a lot more of that later. But I want to introduce it to you in the most trivial case. And so now what I can do is I can just take the log of this. So I can take the log. And of course, what I get is that the log of p of x is now just, n1 times log pi plus n0 times log 1 minus pi. I then go and plug in the parameterization for pi, which is this term here. Goes here and there. I take the derivative with respect to theta, and lo and behold, I get this expression that theta has to be that term here. So theta is the log of n1 over n1 plus n0. Who wants me to explicitly work through that derivative? Okay. Who's okay with what's on the whiteboard, what's on the slide so far? Okay. Good. And I think the other 1/3 is asleep. Okay, good. But basically, if we do this and we plug it back in, we'll see that p of x equals 1 gives me n1 over n0 plus n1. Duh. It's not particularly exciting. This is the thing that you would have done anyway. It's basically, just count the number of occurrences that, let's say, heads occurs, divided by the number of occurrences that tails plus heads occur. Okay. So at least now we have a mathematical reasoning for this. And yeah, okay, here's the entire thing in a lot more detail. Any questions so far? Yes? Okay. So p equals 1. Yeah, okay, so this is an interesting edge case. So my reparameterization made it impossible for me to get p equals 1 unless I get infinity or minus infinity. So if you recall the previous slide, here we have theta is the log of n1 over n0 plus n1. And so what can happen is that I get basically, 0 over, n, and that's 0, and so I get, minus infinity. So things can go horribly wrong. Now let's be a little bit more ambitious, right? We can have n outcomes. Let's say I want to infer where the user comes from. Let's say, logging in from the US or from Canada, from India, UK, New Zealand, China, wherever. So I still want to estimate the data likelihood. Now what happens is, of course, I have, a individual probability for each of those outcomes, pi I. And so what I get is that p of x is no longer, pi times n times 1 minus pi times, n minus ni. But I have, pi I to the ni. And so now I have again, maximum likelihood problem. I want to maximize this quantity here. Or, rather minimize the log, the negative log of this. That's just convention. People like to minimize losses, so we take the negative log of that, and that's what we get. Yeah, of course, we have minus log here. And again, we reparameterize. So the challenge here is twofold. First of all, none of the probabilities must ever become negative or greater than 1. And furthermore, all the probabilities have to sum up to 1. And so we're going to use exactly the same parameterization as what we had before, except that now we have it over many different outcomes. So we have e to the theta x divided by the sum over all x primes e to the theta x prime. And you can immediately see that this has to sum up to 1. Why? Because, well, we are just, normalizing by all the possible arguments that you could plug in for x. And then, again, you take the negative log, you take derivative, you set it to 0. And you will find that you get theta I is the log of ni over the sum over the nj's. So, in other words, we get the thing that we would have done anyway, namely counts divided by total counts. So this must be the most complicated way how you ever derived just taking fractions. Okay.
Just to compare with the previous example, in this example, did we take the product of theta and x?
Correct.
Theta plus x.
Yes. In the previous example, let's go back. So in the previous example, we had pi to the n1, 1 minus pi to the n0. I could also simply have, pi 0 and pi 1, and require that pi 0 plus pi 1 sums up to 1, right? But rather than having a constrained optimization problem in two variables and explicitly writing it out, I just said, well, let's pick one variable and 1 minus that one. Yes, there would be technically an even more bizarre way of deriving a simple fraction than what I did, and I thought I'd just not scale with that. The second thing is, this normalization effectively does what we did there as well, right?
We can't see you breaking.
Okay, so this thing here is exactly the same normalization. So in the case of 0 and 1, this is basically, e to the 0 plus e to the theta 1, or e to the theta, except that now in this case we have, one parameter for each of those outcomes. The logarithm of this will sometimes also be referred to as the log partition function. So, are there any physicists in the room? Have you ever done thermodynamics? Okay. So, if you did this, you probably had something like a state function. And you took the log of the state function and you did all sorts of interesting transforms. That's your state function. And this is about the simplest state function because we have just, one particle and it can be in, k different states. So there's actually a lot more connections that you can use going beyond this simple thing. And so you can actually sometimes get highly surprising algorithms by importing stuff from statistical physics. Yes?
And there, the theta sub I is your estimate?
So the theta I, or theta x, yes. So these are the numbers that I want to infer. They could be my estimates. They could also be the truth.
But when you do the maximization.
When you maximize, these will be my estimates. That's correct. So I should actually have written theta I hat if I wanted to make it very explicit. But I could also simply have a distribution that is parameterized in terms of that. And so sometimes what you will then aim to do is you will want to compare theta minus theta hat. Or you may want to use different measures of computing the difference between those two things. So for instance, the Kullback-Leibler divergence is one of the quantities that you might want to impose to compare two distributions. And we'll get to that as well. So we'll actually see a special case of that probably next Monday. And you'll see more of that when we do variational inference, and you'll probably get an information theory lecture in the tutorials. Okay, but good question. So this theta can either be just the estimate, or it can be the the truth. But if I'm trying to estimate it, then this is what I might obtain. And this again still suffers from that problem of zeros. And let's first see how it behaves in practice, and let's see how far we get in terms of actually bounding things. So let's say I roll a dice, and this is a very, very high precision MATLAB dice that I've rolled 12, 24, 60, and 120 times. And what I've done is I've just written out, how many times you would expect to see various things. So, if I roll it 12 times, of course you would expect that, maybe on average every outcome occurs twice, and it just looks like I got really unlucky and I didn't see anything here. Rolled it, twice as many times and I'm still unlucky, and the 3s are really frequent, and then, you just keep on going. But what you can see is that it's far from, being this very nice, uniform distribution. It's actually quite messy. And most of you would probably not expect that you would need maybe 120 rolls of a dice to get something that's even, within a factor of 2 correct. So look at that. Look at this guy here. We're basically seeing the 5s only maybe 11 times out of 20, out of the expected 20. So, of course, this brings us to the interesting question, do those things actually converge, right? What can we say about probabilities, means, moments, and so on? What are the rates of convergence? So basically, how can we quantify how well we are doing? Can we get worst-case guarantees? And can we use some prior knowledge to, for instance, improve those things? And those are not purely academic questions. They are things that you care very much in drug testing. For instance, if you want to find a new cure for Ebola, you want to find out whether that new drug actually helps or harms people, and maybe that new drug doesn't cure everybody, but just a bit fewer people die. Then you have to ask the question, to how many people do I need to administer this drug before I can actually make any statement along the lines of, well, this probably actually helps rather than hurts. And that sounds like a no-brainer, but there's actually a lot of really interesting research that goes into efficiency testing of drugs. And there's a couple of very nice papers, mostly out of Columbia University, that looked at essentially statistical efficiency tests for drugs, and the results are not pretty insofar as in some cases it's not even clear whether those drugs don't even harm you. So this is more than just an academic pursuit. And the reason why it's not so clear is because of multiple testing and because of people essentially trying to use additional prior knowledge and so on to get guarantees more rapidly than what you would have to do otherwise. We'll see examples of that as we go along. Likewise, in a semiconductor fab, some things can go wrong, sometimes with very, very low probability. And you want to be able to infer what's going on. You want to get worst-case guarantees. You also have this issue in computational advertising. So, for instance, if I am in the business of displaying ads, then, well, let's say you come to me and say, hey, here's a new ad, and I'm willing to bid maybe $10 for you to show it. Then if this ad is a really dud ad, then it's probably not worth it for me to show it. And I want to be able to weed out this ad very, very quickly, right? Because each time I show you a horrible ad, I'm losing money. And I'm probably really annoying the users because they now see a horrible ad and they don't like it and they will not come back. So there's a real cost for me to show something bad, and I need to be able to tell very quickly that this ad is bad. On the other hand, I want to make sure that I didn't just get unlucky and you sent me a really great ad and just the first 10 people had a bad day and so they're not clicking on ads. You have similar issues in user interface design. So when you, for instance, do A/B testing in terms of, let's test a new web page layout. Do the users really like it? How do they respond to it? In those cases, you want to be able to tell very quickly which of the designs is any good. So, camera woman, if you could please press stop, that would be great.